Okay, so today we're going to talk about characteristics of exponential functions. Yesterday we did exponent law. We looked at what happens if I have same base and I'm multiplying with the exponent on all of these things. Today we're going to look at a specific type of function, and the function is called an exponential function. Forget about quadratic. It's a totally new kind of function. So when we start, we're gonna take the piece of paper that I've given you, okay? And if you're looking at that piece of paper right now, how many phases do you see? How many phases? Like how many, not phase, how many layers? That's what I'm looking for. How many layers do you see?
Layers?
One layer, right? No folds, I did not fold it, it's that piece of paper, there's only one layer, okay? Now take that piece of paper and fold it in half. Now, how many layers do you see? Two. So that means if I fold it once, right? One fold, I have two. Okay? That same piece of paper, you're going to fold it again in half. Now, how many layers do you see? Four. Right? Fold it one more time in half. And let's count the layers. Okay? So you're gonna have to be careful because like some of them they're not hot. So you have 1, 2, count with me, 3, 4, and then 5, 6, 7, 8. Do you guys have that?
Yes.
You have 8?
Yeah.
Okay. So if I fold it 3 times, I have 8 layers. Fold it one more time. How many layers do you have now? Now it's tough to count.
16.
16. Do you guys agree that if I had 8 and I fold it in half, that's going to make 16? Right? Okay. Can you fold it one more time?
Yep. One more.
One more. How many do you think? How many do you think?
Double 16.
So what is that?
32.
32. So I have 16 and 16, that makes 32, right? So after the 4th or the 5th fold, now I have 32 layers. If I can fold it one more time, how many layers do you think you're going to have?
64.
What is it? 64, because it's double that. And then if you fold it one more time. Can you? I can't. I'm done.
It's not happening.
It's not happening. But let's say if you can, how many layers do you think you are going to have? 128. How about if you can fold it one more time? How many would you have?
236.
256?
56.
Okay. So what's happening to your number of layers every time you fold?
It's double.
It's doubling. Okay? So that means, even though I can't fold anymore, do you think you know what would be the answer here?
Yes.
What's double 256? 512. And what's double 512?
1024.
So guys, look at this. From one layer, if I fold it 10 times, I'm going to get 1,024 layers. Okay? We started going up from 1, 2, 4, 8. It's like slowly going up. But then what do you notice has happened once my numbers got bigger? Was it still getting bigger at the same rate, or was it getting bigger faster? Getting bigger faster. You see that I jumped from 500 to 1,000. Okay? Or I jumped, if you look at the beginning, you have 2, 4, 8, but then it jumped fast. Okay? So that's what's folding the paper. All right? We said know that it's doubling. Okay, so we're double. Now, do you guys remember the first difference?
Yes.
Okay, what's the first difference? What do I do with the first difference? What do I do with my first difference? What does first difference mean? You subtract y2 minus y1, right? So you take your y values and you subtract y2 minus y1. Okay? So my y values are the number of layers. Let's subtract. What's 4 take away 2? 2. What's 8 take away 4?
4.
16 take away 8.
8.
32 take away 16.
16.
64 take away 32.
34. Oh, that's fun.
128 take away 64.
64.
You caught it? Now 256 take away 128. 512 take away 256.
256.
1024 take away 512. And I can't do the last one because I don't have any more numbers. So is your first difference constant? Is it the same number repeating?
No.
No, right? It's not 1, 1, 1, 1, 1, 1, 1, or 2, 2, 2, 2, 2, 2, or 4, 4, 4, 4, 4, right? They're different numbers. So the first difference is not constant. Okay? What do I do for the second difference? Because we learned with quadratic that if it's not, the first difference is not constant, you can try the second difference. What do we do with the second difference?
Same thing.
Same thing, taking my first difference, pardon me. So taking my first difference and subtracting, right?
Yeah.
So 2 take away 4 is? 8 take away 4 is? 16 take away 8 is? 32 take away 16. Yeah, we're not getting out of this. And then 32, and then 64, and then 128, and then 256. Is my second difference constant? No. So, but I'm stuck right now. Neither my first nor my second. So it's not linear, it is not quadratic. And this is all what I know. Right? So now, there is a different way. We're going to have to look if it's exponential, because that's what we're learning. To do the exponential, eyes on me please, because this is very important. To know if it's exponential, you're going to have to do what we call the first ratio. Do you guys know what the word ratio means?
Compare. Like,
Say that out loud a little bit.
combine.
Divide. Difference means subtract, right? Ratio means divide. So what I'm doing is, I'm going back to my original y values, and I'm dividing them. Same way as I was subtracting, but I'm dividing in this case. Okay? So, I'm going to go back to my y values, and I'm going to divide to find my first ratio. Okay? So, for the first ratio, it's y2 divided by y1. Okay? So, what's 4 divided by 2? What's 8 divided by 4? 2. What's 16 divided by 8? 2. Right? What's 32 divided by 16? What is 64 divided by 32? 2, 2, 2, 2. So what did you notice about the first ratio?
It's constant.
It's constant. If your first ratio is constant, that means it's an exponential function. Now, do you guys know why my answer is 2 or why my ratio is 2? What was happening to your layers?
It's doubling.
They were doubling. And double means 2. And that's why my ratio is 2. If they were tripling, what do you think your ratio was going to be?
Tripling.
3.
Tree.
Right? So it all depends, the ratio Depends on what's happening with your exponential function. I don't know what happened here. Okay. Okay, so you see right now with exponential, first difference, second difference, they don't make a difference. It's the ratio that makes it. Okay, the ratio's constant. Now we looked at the table of value. Let's also look at what happens if I graph. How is it gonna look? Linear, how does it look like? How does a linear function look like?
Straight line.
Straight line. How does a quadratic function look like?
U-shaped parabola.
U-shaped parabola, open up or open down, parabola, right? Let's look at how would an exponential function look like. Okay, now, first I have to plan. X values, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, perfect. It's easy to find. The Y values, on the other hand, 2, 4, 8, 16, 32, I have to fit up to 1,024 on my graph. Okay? Plan ahead of time before you graph your points. Look at your X and Y values, see what you have. So, if I'm looking at plotting this here, right? So I know for my X values, it's easy. It's 1, 2, 3, 4, right? That's easy. The problem is, what scale do I pick for my Y value so I can fit as many points as I can? If I go up by 1, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'm going to end up there, and I'm going to only be able to fit 3 points. Is that a good representation? No. If I go up by 5, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, I can fit maybe 4 points. Is that a good representation? No. So I have to pick something that's a little bit bigger. Okay? Let's go by 10. Okay? Let's see. So if I go by 10, I might have to squeeze the first 3 points, but then after that I should be fine. 20, 30, 40, okay? Now, right here I have the number of folds, labeling your axis, and right here I have number of layers. Okay, so let's see what we have. 1, 2, right? If I go back to my table, I have 1, 2. So 1, 2 is going to be somewhere right here. How about 2, 4? 2, 4. 3, 8, getting closer to the 10. 4, 16. Do you guys know where I'm getting the numbers from?
Yeah.
So if you go back here, I'm looking at 4, 16. Now I'm looking at 5, 32. So 5, 32. 6 was 64. 7 was 128. Even this one is like pretty, I wasn't able to fit all my points, right? But at least it's a good representation, okay? So if I'm gonna graph this, how many folds, how many layers did I have if I had no folds?
1.
1. So at 0, where would it be?
Right there.
Right there, okay? Close to the 0, 0, but it's not. Okay, so let's try to get these points all nice and lined up. So what do you see here if you're looking at this graph?
Curve.
It's a curve, right? It's not a straight line by any.
A slow and then gradual curve.
It's a slow and then gradually increase, okay? You might think it could be half of parabola, but it's not. It's not. Because what happens is, yes, it does look like it, but it's not. Eyes on me for a second. So if I want to go into the negative, which kind of doesn't make sense in this scenario, but let's look at it. So what I was doing is I was folding, okay? Instead of folding, I'm going to rip, okay? So if I rip this in half, how much of the layer do you still have? How much of the layer do you still have? Half of it, right? If you rip it again in half, how much do you have right now? 4. If you rip it in half, you have 1/8. Just make it easier for you. If you rip it another time in half, you have 1/16. So these numbers are very, very small numbers. So it will be 1/32.
I will say a piece.
And it will be 1/64. And it will be 1/128. And then it will be 1/200. So if you do 1/128, that's 0.0 whatever, right? So it's smaller and smaller. Are you ever gonna get to a 0?
No.
No. You're gonna keep ripping. You're gonna keep you're gonna have a piece of a paper, right? It's a very small piece of a paper. You might have to go microscope, but you can still have a molecule in there. Okay? So no matter how many times you rip, you're not gonna get to a 0. So that means if I'm going to actually extend, if I'm going to extend to the negatives where I'm actually ripping, this graph is gonna extend, but it's gonna extend like this. It's gonna be flat and it's gonna get closer and closer to the 0, but it will never touch that 0 line. Okay? Now you don't see it, but if I actually expand it, even if I expand here, you will not see it. But if I actually expand a real graph, right? That's graphed by a technology, right? You're gonna see that the number keeps getting smaller, but then what's the difference between 0.5 and 0.25? It's only a 0.25 right there, right? Which is very minimal compared to going from 64 to 128, right? Minimal. So that's why you don't see it. Okay? So if I'm looking at an exponential, if I want to look at this, if I want to describe this, how would you describe it to me? Describe this graph for me.
Slow, then gradual increase.
Slow increase and gradual increase. Can you describe it in any other way? Flat on one side, right? Horizontal on one side, right? And then a fast increase on the other side, right? So you can say slow increase then a fast increase, or you can say flat horizontal on one side and then a fast increase on the other side. Okay? You'll always have with exponential, you'll always have this scenario. Doesn't matter which way it goes. You will always have something fast and then slow. Okay? Something fast, slow, and then something fast. No matter which way, which direction it's going, you're always going to have a horizontal and a fast. Horizontal and something fast. Either decrease, increase, whatever it is, there's always going to be that scenario. Okay? So these are other exponential graphs. We'll talk about them later. Do we understand that? All right. Now, let's answer these word problems. Not word, these, whatever, questions. Thinking questions. So, can you guys answer the first question for me? Describe how the number of layers changes as the number of folds increase.
With each layer, the number doubles.
So the number doubles. Can you, so grows fast also, we can say, that it grows fast. Okay. So doubles each time. Grows exponentially or fast. So we did calculate the first and second difference in the table. What did you notice?
Difference are not constant.
The first and second difference are not constant, right? If you go back to the table, right, if I go back here and I scroll back here, they're not constant. Have you noticed anything else other than they're not constant?
They're mirror images, they're duplicate, like the numbers are the same.
So they're the same as the y values, right? 2468, 248, sorry, whatever. Right? 248, no matter what. Right? So, yeah, good. So, let's write that. So differences are not constant. They grow just like the y values do. Right? So if you go back, you see that as 248, 16, 32, 248, 16, 32. Okay, so do you notice a pattern in a table? Describe it. Can you create an equation to represent the relation? So what did we say about the number of layers? What was happening to them? What was happening to the number of layers? They were doubling. Okay, so the pattern is that they were doubling. Okay, how about if, what was happening to the x values, which is the number of folds? What was happening to the number of folds? Going up by 1. The number of folds is going up by 1. The y value is doubling. Okay, so let's write that down. So the x values goes up by 1 or increase by 1. And the y value pattern doubles. When I say doubles, that means I multiply by 2, right? So, first time I had the 2. Okay, so when x is 1, I had the 2. Seriously. So if I multiply this by 2, so when x is 2, I multiply this by 2, what do I get? 4. How about when x is 3? I multiplied this by another 2, right? So 2 times another 2. Right? Because this, I'm just using this as an example, just because I want to show you a pattern. Okay? When x was 4, I took the 2 times the 2 times the 2, and I multiplied it by another 2. Do you see the pattern here?
Yeah.
So that would be 2 to the power of what? 1, 2, 3. Right? This would be 2 to the power of what? 4. What do you think the 5 is going to be? 2 to the power of 5. What if I have 30 for x? What would it be? Huh? 2 to the power of 30. So how would I write that as an equation? 2 to the power of whatever x is. So 2 to the power of x. Right? So if I want to write this as an equation, I can write it as y is equal to 2 to the power of x. Whatever x is, I'm doubling. So I'm multiplying by 2. 2 to the power of how many times? Okay? So go back here. This is 2 to the power of 1. Go back here. It's 2 to the power of 2. Right? This is 2 to the power of 3. 2 to the power of 4. If x is x, I don't know what it is. It could be 100. It could be 120. It could be whatever. 2 to the power of that. Make sense? What did we say about the first ratio? It's y2 divided by y1, right? What did we notice about the first ratio? Something that you guys are going to relate to later on, but it's important to see it right now. What was your first ratio on the table? 2. What's your base of your function here? They're going to always match. So whenever you write your function, your ratio is the base. So if your ratio was 3, then your base is going to be 3. If your ratio was 4, then your base is going to be 4. If your ratio is 500, then your base is going to be 500. Okay? If your ratio is 0.5, your base is going to be 0.5. So the base of the equation. Now, we're going to talk about this. We're going to talk about this later, but I would like to take it up right now. Your equation for exponential is y equals to b to the power of x. We're going to talk more about this later, okay? This is what exponential means. Exponential means the exponent is a variable. The exponent is your letter, okay? So, a is your initial value. In this case, our initial value was 1. I feel like I'm spelling this wrong, even though I write it 500 times in a day. B is your base, and that represents your ratio. Okay? My initial value here was 1 late. So I don't have to write 1 because 1 is invisible. Okay? But my base, which my ratio was 2, because it was double. And then to the power of x because that's an exponential. Okay? We're going to cover this in more details. But remember this formula. This is the formula for exponential functions. Did we finish copying this? So, 3 things that we're going to compare right now. Linear, quadratic, which we've already compared these in the previous lesson. Now we're going to add to it the exponential. So, do you guys remember the equation of a linear function? Y equals what?
Oh, wait.
All right? This is the equation of a linear function where you have a degree 1. Y equals mx plus b. Can you give me a quadratic relation? The standard form.
Y equal a bracket x minus a.
Okay, that's the vertex form. Give me the standard form.
Oh, y a squared plus b squared plus c.
Okay? So we're looking at the standard. Which is, it's not wrong to give me the vertex form, but I'm just looking for the standard most expected. Now with the exponential relation, your equation is going to be y equals a for your initial, b to the power of x. What's going to be constant if it's linear in the table of value? The first difference. If it's linear, it's first difference. What's going to be constant if it's quadratic? The second difference. What is going to be constant if it's an exponential? First ratio. How your graph is going to look like if it's a linear function? Straight. Which is an example of it. What would your graph look like if it's quadratic? Parabola. So it could be open up or it could be. Now, for an exponential, one side is almost horizontal. Or flat. While the other side grows or decays fast. So you're going to have horizontal and then increase, right? So that's one example. Or you can have an example where you're decreasing fast and you're horizontal. As long as one side is almost horizontal and the other one is either increasing or decreasing fast.